Welcome back to the Bal Vigan Bharti, and this is your mentor Abhilash Sarkar. As you know, in the last chapter we are ended there in discussing the Pascal's law. There in the Pascal's law that we have learned in a fluid that is kept in a vessel, pressure created by giving additional force on the system on the fluid is being transmitted into the fluid in same manner, that means without diminishing its value, in same manner in every directions, on all directions. So that means if I give an example, that a fluid is kept in a vessel, and any point of which if I put a additional force by which it will turn a pressure, let's say 2 bar, it will be transmitted without diminishing its value. That means 2 bar is added to the existing pressure. Let's say the existing pressure is 4 bar, that altogether 6 bar pressure will be transmitted into the fluid inside that vessel in all directions. That can be experienced if I able to get any tapping out of the vessels, and to measure the pressure I will get 6 bar pressure anywhere in the vessel in any directions, whether it is from the bottom, whether it's from the side or the inverted one, anywhere. If you measure the able to measure the pressure, it will be of 6 bar. So that means from there we have established some you can say uh, application of that Pascal's law in hydraulic lift. In hydraulic lift, there is an arrangement where if I put a small pressure at one arm of the system, I will get a increased increased force increased force due to the increased pressure into the system. So that means where I am putting a force F1 here, which is comparatively less and the cross section here in this arm is, let's say, A1, and due to this pressure the liquid column has come down by this H1, which will give in turn a force which is being created on the other arm, let's say F2, and F2 is much more higher due to its cross section A2, and at the same time the fluid column will increase by another H2. So from there we have understood that if I equalize the pressure, because this is a closed vessel, and the fluid inside is incompressible because we are working with the ideal fluid. If this is the case, then F1 by A1 is equal to F2 by A2 by equalizing the pressure. From there we have established F1 by F2, that is equal to A1 by A2. So this was and then after we have equalizing the volume flow rate is equal, because we are not losing any liquid out of the system, neither we are putting any fluid inside the system. So that means the whatever volume transmitted due to this force down, if I calculate it with the cross section into the height, that is the height is the displacement of the fluid column, whatever liquid is being transmitted from this arm, it will be accommodated in the other arm, and due to that, if I assume that volume flow rate due to the incompressibility of the fluid, it will be same from there A1 A2, and that is being transmitted into this equation. This also can be done in other way, because this is due to equalizing pressure. Okay, so from there this is being transmitted. Now another concept can be at the same time can be accepted, where if I say whatever force is being inserted is given into that, due to that whatever work being done into the system that is force into displacement will be transmitted into the other arm, because there is no other energy is coming into the system or going, so that energy is conserved here. Energy is conserved. So any system, if energy is conserved, then the work done in terms of the energy. What is energy? Energy is nothing but the rate of doing work. So now this is the work done, and that is being done at the same time. If I say that force, this exerting force and reaction, it will be existing for the same time. So that means rate of doing work for the time it is doing, at the same time I am getting the work done on the other arm for the same time. So time is not the criteria which will distinguish the work being done or energy being transferred. So energy is consumed in any system, because energy cannot be created nor destroyed. So whatever with the energy in the system, that will always be conserved. From that concept, energy is work done by time. So this is not affecting, because this is the very this as because this is incompressible, so there is no time loss in between transferring, because for the time it is starting moving and reaching some height, this response is immediate. There is no time lag between this two, so there is a balance in the work. So from there also, F1 by F2 is equal to H2 by H1. So that also, if I equalize, I will get this. If I equalize, because this part will be equal to this part, so A1 by A2 is equal to H2 by A1 H1. So A1 H1 is equal to A2 H2. So with this concept, where energy is conserved in a system, I can say that what is this? This is volume flow rate in the arm 1, cross section into height, a volume flow rate in the arm 2. So if if I use the Pascal's law for an ideal fluid, and if energy is conserved, that means it is incompressible, so then volume flow rate must be same. So whatever you assume earlier, that also be established by considering the ideal fluid and the ideal conditions. Okay, so overall, this in a hydraulic system or whatever applications you will apply the Pascal's law will be there. The volume flow rate will be same. Okay. And volume flow rate same, that can be also said to be the mass flow rate, because the rho, this is the same fluid is being transported, so that mass flow rate will also be same in this case. Okay, volume flow rate or mass flow rate will be same. So this has gone the Pascal's law and its application. Now we learn buoyancy. Buoyancy, that in turn can also be represented upthrust. Now this word is very much clearing your concept, that upthrust means some thrust which is acting upward. So what is that? So as per definition, the buoyancy is the force acting on a body which is partially or fully immersed or immersed or submerged into a fluid. So that means if a liquid is if a means fluid is there and any body is submerged, so this body will experience a upthrust by the fluid where it is partially or fully immersed, that force is called upthrust, and its value is equal to Vf, rho f and G. What is Vf? Vf is the volume of the fluid dispersed. Volume of the fluid dispersed. That means when it is dipped into the water, whatever volume it will separate out due to its own volume, because it will occupy some space. So in that space no fluid can exist, it will occupy that space, and that will be dispersed elsewhere. So whatever volume it dispersed, that volume into the density of that fluid where it is dipped and the gravitational force. That means ultimately what is that? This is nothing but mf into G. That means the mass of the fluid dispersed into G. That means the weight of the fluid dispersed. So the buoyancy is nothing but the equal to the fluid dispersed, the weight of the fluid dispersed. Now with this concept, a theory that is named after Archimedes. The name after Archimedes is arrived. Archimedes theory. So what he has said that the language is such that when a body fully or partially, it may be reversed, partially or fully, partially immersed into a fluid will experience a force which is equal to the weight of the fluid dispersed. Okay, so this is the theory where he said, as I explained earlier also during buoyancy, the fluid which is being dispersed by him, by the body dipped in a fluid, will be the will equal with the equal to the weight of that fluid. That means if I say fluid dipped and this much part is dispersed, so now the buoyancy or the upthrust, if I represent it with U, sometime it is B, somebody has also represented B, so that is equal to the volume of the fluid dispersed into the density of the fluid dispersed into the G. That means he is saying W, so W can be written as the mass of the fluid into G. So mass of the fluid is volume into fluid into, so that is there. Okay. Okay, fine. Now on this concept, if I further move, so that means this force, this is exactly a force, it will force act on a body which is being dipped into a fluid. So that means this body if I say this has some own weight, if Wg, which will be equal to the volume of the solid, and that it has some density into G. This is the actual weight or the weight in air. So that means any matter, if it is kept in air, that is the weight of its own, and that is only being affected by the buoyancy of the air. That is, we are saying for everybody it is negligibly small. So weight of air is assumed to be the weight of the body itself. we are not considering the buoyancy due to the air. So if this is the weight of the air, and when it is dipped inside, you will experience due to the density of the fluid. If it is much more than the air, then it will experience additional force which will acted upon this body upward. The upthrust or the buoyancy will and the weight will act downward. This is so that means with this force, if it is balance, if it is the body is equilibrium, there must be then resultant force. So resultant force it is, we call it the effective weight of the body. It is the resultant force, effective weight of the body, which is equal to the weight of the body in air minus the thrust, because whatever the effectiveness of the weight, that is reduced only due to this part, because in air, if it is lift up in the air, it will only be this part, there is no upthrust. When it is dipped, this is reduced, as because this is in the opposite direction. So that means the effective weight of the body, that also can be done. If I say, if I have spring and this is being having a dynamometer which is showing the weight of the body. If it is earlier dipped outside and slowly it is dipped down, you will get the deviation there, and this will be equal to this, whatever after dipping inside into the fluid, whatever value will show, it will be this value directly, and this value when it is lifted up into the air, you will get. So you can, from that you can automatically get the upthrust value, and upthrust we know. now if I put this into the equation, all this whatever I am saying, that effective weight is equal to air minus upthrust. Now if I take and to put it in shape, 1 minus upthrust by W air. Okay. This will be the case. Now if I consider a case where body is inside the fluid, fully submerged, fully immersed, if it is the case, then how the thing will change. Okay. First I will consider the fully. So the effective weight will be the air, and upthrust is Vf, rho f and g, and the weight in air Vs, rho s into g. This is the fluid dispersed, this is the actual weight. So ultimately 1 minus Vf, rho f, Vs, rho s. Now if it is fully dipped, that means Vf is equal to Vs. It is nothing is outside the fluid, so that means this will cancel out. It will ultimately 1 minus rho f into rho s. So this is the condition when it is submerged. So next, this can be changed into other form also according to your requirements, but ultimately the effective weight when it is fully submerged will be given by this. Now on this equation, the condition of floating or sinking will discuss, because there could be some condition for which the scenario will change. The first of the condition, which is very straightforward, if rho f is equal to rho s, if the fluid on which the solid is being dipped, if their density are same, then what is the result? WE, this is equal to 1, 1 minus 1, 0 is equal to 0. When this condition can arise, if I starting from the initial equation, where WE is equal to W air minus U. Now if this part is 0, so that means W air is equal to upthrust. That means whatever buoyant force is acting on upward and downward its weight, it is balancing each other. There is no residue force acting on it. In this condition, where this body will float, it is definitely will float. It will not sink. So it will float by touching the surface of the fluid. It will just touch the surface of the fluid and it will float. And this is the condition when the CG and buoyant force, the buoyant and CG force will act upon in a single point. Remember this buoyant force or upthrust and the weight of the body will be aligned in, definitely always aligned in the same line, but in this case that will act in a single point. There is no distance between these 2 points. Buoyant force and the weight of the body will act upon a single force. So it is the most stable. Now if you want to put a force, it will start rotating. Not stable, I am saying. In this condition, this is much to the point, and if I put any force either side, it will start rotating in its point. It will not trying to come to, if I say this is the topmost point in this condition, it will not try to come up in the same location. It will start rotating, and when due to the friction of the fluid column, it will stop. Okay, so this is the case. Okay, and this also happens if the body is partially submerged and body is uniform, then also it could happen where the buoyant and the weight of the body acting in the same point. So this is the first condition. Second condition, it could happen that fluid is less than solid. Okay, the fluid density is less than solid. That means this part, this F by is less than 1. So WE will be more than 1. So that means what is WE? That means W air will be more than upthrust. So that means if the force which is acting downward, it is more the force upward. So there is a imbalance in force downward. So that means the body will try to come down. So this is the condition of sink. So that means body will try to come down. It is a condition of sink. Now third condition, when VF is greater than Vs, the fluid density is more than the solid density. Then that case this will be less than 1, because if it is greater than 1, it is almost negative. How come it is negative is possible? So this WE is a figure, actual figure. So that means it means it cannot be negative. So basically it is less than 0, I can say. Less than 0 is not possible. That means what is happening here, U is more than W. If it is because the effective weight, this is the mod value of air minus U. Okay, there could be possibility the upthrust is more than the weight of the body, then it will not allow it to come down. So in this condition, what will happen? It will when it is sinking, and in this condition it will partially or sometime maybe fully floating on the condition of is upthrust, the upward force. If it is more than the weight of that, there is an imbalance force which is acting upward. So that means it is a condition of float, and that float can happen, it will partially or fully floating. It is depends on the force. If it is force, it can overcome this completely, and there is not allowing any the fluid to disperse. Okay, so this condition can be partially or fully floating. Okay, but the condition of float is when the density of fluid is more than the density of the solid. Okay, you might have experienced, if I take any semi-solid, that means it is a form of liquid, is so thick I cannot, if I want to say, or any hollow ball, plastic ball, very lightweight ball, or a balloon, if I throw into the you can say water, it will be on the floor itself. It will not able to come down into the fluid. So this is the condition where the ultimate condition, it will not allow any part of the solid to dip into the water. The upthrust is much more than the weight of the body. So this condition may come, but that this is the condition of float. This is not the negative value, rather this is the result of the difference of these two. So if in case U is more than W, that this will seems to be negative, but will always take. So in that case, what is the effective weight of the body? Effective weight will be none. You will not get any force in the dynamometer. If we able to hang it with this dynamometer, will not get any weight. Okay. The next, okay. The next is law of float, because in one condition only the thing is fully submerged but floating. So law of float says the condition where the body is fully submerged and floating. So this condition where rho of fluid, density of fluid is equal to density of solid, we have taken. So that means here, what do you say? Upthrust is equal to the weight of the solid. So upthrust is equal to what? Vf rho f into g, and the weight of the solid in air, this we have represented earlier. So Vs rho s into g. So g is value, it is applicable for all the cases. So g can cancel out. So Vf by Vs is equal to rho s by rho f. Okay. So this is the condition of float. Condition of law of flotation, or you can say the equilibrium. That means the F net is equal to 0. That we have taken because F net is nothing but the effective weight. F net is nothing but the effective weight, which is equal to the, in this case, Ws minus U. The net force, if these are equal, so that means the net force or the effective weight is equal to 0. There is no additional force. In that case, that Vf by Vs is equal to rho s by rho f. Okay. And this don't be confused, because this is the only condition. This condition only arrives when the body is completely submerged. This condition is for completely submerged, and the volume dispersed by the body is equal to the volume dispersed, volume of the body is equal to the volume dispersed, the volume of the fluid dispersed. So then only this this can be applicable. This is the condition of the unique floating condition, where it has completely deep into the liquid, okay, completely immersed. But this condition is not always that it needed to be, because it can happen that a body is partially immersed, still it is floating, partially immersed and still it is floating, because the volume it will disperse by the liquid, that the density is such that there could be other conditions where this will satisfy. Okay, this equation can be satisfied for not only v mu, that density of solid is equal to density of fluid. This is a unique condition where volume must be same. But the law of flotation is that if the buoyant force and the weight of the body balances each other, so that means it, in any condition, immediately if you dip, it will be in a steady condition. Otherwise, if any imbalance is there, it will come up or come down, it sink down. So that means if I say in this condition, if I want to put another force here, it will slowly will come down due to this imbalance of force. But when it is being removed from that body, it will start to initial condition, as because the force is absent. So when you go down, let's say I am putting this force and the body is compelled to be somewhere here. So what is happening? Due to the force, this is going down. That means there is a imbalance of force. This is due to that force minus u. But this u will not be same as u if in the absence of the force. This will be u1. Till it is there, it is causing to the body to go down. But at the same time, u will increase from u to u1. How it is increasing? The initial u, when it is in this condition, maybe the Vf and rho s and g, this is the value. But when it is deep down due to the additional force, it will be some volume will change. The disbursement of the volume in this condition will not be same when it was there in the surface, and this Vf into g. So this value definitely will be more than this. Now when it is not there, so now the imbalance force will be reversed. U1 will be more than, because unless this was there, the Ws is equal to U. But now it has increased. So imbalance force is acting upward. So it will bring the body to the surface where it will be perfectly in equilibrium. Understood? So the condition of floating is only that the net force is zero. This is a unique condition if it is completely some immersed, and what could be the case. But there are possibilities that the solid may float at anywhere, partially dipped or fully dipped. This is the theory of the Archimedes. Okay, so the law of float is being established by this this condition. Okay, the volume of fluid by volume of solid is equal to reverse, that is volume density of solid by density of fluid. Okay, so this could be if the body is cylindrical. So these are the some unique cases where body, because cylindrical body, what is the, how you can calculate the volume? You may calculate the volume by this. Okay, if it is the length of the cylinder, and if it is r has the diameter, so you can solid can be calculated by pi r square into h. If it is spherical, then 4 by 3 pi r cube. Some uniform body, you know the how to get the volume. So from that volume you can calculate the volume of solid, and accordingly you will get the volume of the fluid. That is very much dependable. And yes, what we are saying, if it is a uniform body and the orientation of the body, when it is dipped inside, it is just kept vertically down. So in this case, that volume is equal to what? The cross section A volume is equal to the cross section A into the height of the body. And the same way, it is the liquid also be dispersed. The volume of solid is cross section into the total height, and if the liquid disperses, let's say h1, so that volume, the fluid is equal to the cross section into h1. So then with the similarity, this is some specific condition if it is completely vertically dipped and in equilibrium it is straight, it is not roaming here and there. So in that case, you can put the volume of the fluid is A into the column of fluid dispersed, A into the actual height of the body. So it is equal to rho f rho s by rho f, and this can be established like that. This is a unique case, and accordingly you will get. But whereas in the spherical is a body which has all dimension, it is in all direction it is same, so you cannot establish the volume will be the volume you have to consider for this case. This is a unique case. Okay, I am not going to that part, you can do your own, I understand. But one thing, what is the, if I want to disturb the equilibrium in case it is floating, the floating, there could be three possibilities. If the buoyant is acting at a point, this is the upthrust, and the center of gravity acting in this point CG is the, if the buoyant point and the if condition 1 I am saying is the upthrust point is above CG, what would be the case? Now if it is the case, okay, now if I try to rotate it by a force, whether it will be in equilibrium or it will disturb. Now when I put a force anti-clockwise, so that means this line of force will deviate from this, and this point will shift to some point here, and this point shift to some point there. Now buoyant is always acting upward and the weight is acting downward, so that means this will create some what, a torsion. So that means it is the line of force of U, this is line of force of weight. So these forces are acting. So what they will try, they will give a torsional force, a rotational force, and it will try to bring the body in the same position as it is there. And if I want to disturb with the force this side, so the thing will happen same way. It will be, the point will shift here, this point will shift here, but the buoyancy will act here, and weight will come will act downward, and this force together it will try to move. So this is the condition. If the buoyant point is above the CG, so it is the most stable condition of the body. Okay, so now when it will happen, the buoyant, if it is acting above the CG, so that means this case arrive case arrived when body is mostly immersed. His body is mostly immersed. This means maximum part of the body is immersed into the fluid where it is dipped. So in that case, the buoyant point will be there above the CG, because the body CG of the body is somewhere. Now if buoyance has to be the on top of that, so that means the liquid and the fluid that has to be dispersed will be more. So in the most dipped condition, it will be the stabilized one. So that means a body, when it is fully submerged, whether it is just floating or sink, it will be the most stable condition. Understand? Now how can I establish this fact? If I consider the other fact, when when the body is floating and its CG is above if the body is floating this way, and if I consider CG is there in the same line, CG is there and the buoyant is there. This is upthrust point, this is CG point. Now in this condition, if I am to disturb with any force, so in this case, this will be this and this point will be transferred there. This point accordingly will be transferred here. Now you see, weight will act from this point downward and buoyant will act this point upward. Now with this imbalance force, what will happen? Whether it will try to doing this or it will try to turn this way, this will try to turn this way, because this force is acting, and here the force acting is, this is buoyant force and this is weight of the body. So this will try to turn, it is further it will unstable. With a small force, if I can disturb the line of the force, it will try to topple the object downward. So that means it is not able to keep it in its own position. So that means whenever there is a buoyant force acting below the CG, this is the unstable condition of the body keeping it in equilibrium. Understood? And so that means this point will happen when the body is very little submerged into the fluid. Okay, so what next it is? Okay, now one condition when a body is in some two layer of fluid, let's say there are two layer of fluid, this is some fluid, this is some fluid, and the body is there then what would be the equation of this? This will disperse this liquid, so and it is in stable condition. That means the weight of the body must be equal to the as per the theory, the fluid dispersed this part. That means if I say this is the fluid 1, this is fluid 2, volume dispersed, so the volume 1 into the density of the fluid here into G, this is equal to the volume 2 into the density of 2 into G, and in turn this will be the volume of solid into density of solid into G. So G cancelled out, ultimately V1 for liquid, it is not in same fluid, it is having two layer of fluid, but these are fluid which is immiscible. If it is immiscible, that is not mixing to each other. If it is mixing, so it automatically will make a one solution, and there is the density will change into by what is the ultimate density? Total mass of those liquid divided by the total volume of those liquid. By this we can get the cumulative density when the liquid will mix each other, and from there we can establish this equation by taking this is 3. So then your volume of the liquid, ultimate liquid, will be this, and if it is rho into G will be the weight of the solid. So this way you can come to the point. So this is, I suppose, end of the theory that has to be covered in fluid statistics. We will move on to the theory, move on to the problem solving session. If not any other I left, I will see it. If any theory is to be discussed, I will discuss. Otherwise, I will move on to the problem solving session. So thank you for now.